This research paper presents a novel method for real-time 3D shear wave absolute vibro-elastography (SWAVE) using a matrix array transducer. The SWAVE technique leverages an external vibration source to generate mechanical vibrations within tissue, which are then estimated and used in solving a wave equation inverse problem to provide tissue elasticity. A matrix array transducer, paired with a Verasonics ultrasound machine, acquires 100 radiofrequency (RF) volumes in just 0.05 seconds at a frame rate of 2000 volumes per second. This ultrafast acquisition allows for a substantial extension of the possible SWAVE excitation frequency range, now up to 800 Hz, enabling new tissue modeling and characterization. The proposed method uses plane wave (PW) and compounded diverging wave (CDW) imaging methods to estimate axial, lateral, and elevational displacements over 3D volumes. The curl of the displacements is used with local frequency estimation to estimate elasticity in the acquired volumes. The technique was validated on 3 homogeneous liver fibrosis phantoms and 4 different inclusions within a heterogeneous phantom. Results from the homogeneous phantoms showed less than 8% PW and 5% CDW difference between the manufacturer values and the corresponding estimated values over a frequency range of 80 Hz to 800 Hz. For the heterogeneous phantom, the estimated elasticity values at 400 Hz excitation frequency showed average errors of 9% PW and 6% CDW, compared to the provided average values by MRE. Additionally, both imaging methods were able to detect the inclusions within the elasticity volumes. An ex vivo study on a bovine liver sample showed less than 11% PW and 9% CDW difference between the estimated elasticity ranges by the proposed method and the elasticity ranges provided by MRE and ARFI. The 3D ultrafast SWAVE method introduces a novel approach to real-time image acquisition for estimating tissue elasticity, utilizing a matrix array transducer. This technique extends the excitation frequency range of SWAVE up to 800 Hz, enabling more comprehensive tissue modeling and new applications. The imaging setup consists of a signal generator connected to a voice coil shaker, which generates sinusoidal vibrations inside the tissue, and an RF echo data acquisition system at a sampling rate of 20 MHz. The method utilizes frame rates of 2000 volumes s to acquire 100 RF volumes in 0.05 seconds, significantly reducing the impact of unwanted motions due to breathing or transducer motion. To validate the technique, 3 homogeneous liver fibrosis phantoms with different elasticity values were used, representing the range of healthy livers to those with fibrosis and early cirrhosis. An ex vivo study using a bovine liver sample was also conducted to compare the range of elasticity values with magnetic resonance elastography (MRE) and acoustic radiation force impulse (ARFI) methods. The study aims to investigate the consistency of the elasticity ranges measured with different methods and to identify possible future work and study limitations. This research paper presents a comprehensive analysis of the interplay between quantum computing and machine learning, 2 rapidly evolving fields that are increasingly intertwined. The authors delve into the potential synergies and challenges that arise when combining these technologies, providing an in-depth examination of their intersection. The paper begins by outlining the fundamental principles of quantum computing, which leverages the principles of quantum mechanics to process information in fundamentally different ways compared to classical computers. It then explores the basics of machine learning, a subset of artificial intelligence that enables systems to learn from data without being explicitly programmed. The authors discuss how quantum computing can enhance machine learning algorithms, particularly in terms of speed and efficiency. They highlight several quantum algorithms that have been developed to solve specific machine learning problems, such as k-means clustering and support vector machines. These quantum algorithms offer significant speedups over their classical counterparts, potentially revolutionizing the field of machine learning. However, the paper also addresses the challenges that arise when integrating quantum computing and machine learning. One major hurdle is the noise inherent in quantum systems, which can lead to errors and inaccuracies in machine learning models. Another challenge is the limited availability of quantum computing resources, making it difficult for researchers to access and utilize these technologies. In addition to these technical challenges, the authors also discuss the conceptual hurdles that must be overcome. For instance, many machine learning algorithms rely on classical notions of probability and statistics, which may not directly translate to the quantum realm. Furthermore, the authors argue that there is a need for new theoretical frameworks and tools to fully harness the potential of quantum machine learning. The paper concludes by highlighting the promising future directions for this burgeoning field. The authors emphasize the importance of interdisciplinary collaboration between quantum physicists, computer scientists, and machine learning researchers to overcome the challenges and realize the potential of quantum machine learning. They also suggest that further research is needed to develop more robust quantum algorithms and to better understand the theoretical foundations of quantum machine learning. Overall, this paper provides a thorough exploration of the intersection of quantum computing and machine learning, shedding light on both the opportunities and obstacles that lie ahead. The novel method for 3D curl calculation in ultrasound elasticity imaging involves a combination of diverging waves and the GLUE 3D algorithm to estimate tissue displacement. This technique generates virtual sources behind the transducer, adjusts parameters for smoother displacement maps, and fits displacement phasors using a least squares solution. The curl calculation process projects axial, lateral, and elevational displacement phasor volumes onto a fine 3D grid with a step size of 0.05 mm, equivalent to the axial resolution of the beamforming grid. The curl of the 3D volume is estimated using partial derivatives of the displacement phasor in axial, lateral, and elevational directions, resulting in 3 volumes that provide insights into tissue mechanical properties. The method's accuracy is demonstrated through experiments on phantoms and ex vivo data, showing that changes in GLUE 3D coefficients by 100% result in elasticity value changes of less than 2%, indicating robustness to parameter variations. This technique can accurately estimate tissue displacement and mechanical properties, making it a valuable tool for diagnostic imaging applications. The authors present a methodology for 3D ultrafast shear wave absolute Vibro-Elastography using a matrix array transducer. To estimate the local spatial frequency of the shear wave propagation pattern, the curl operation is applied to the displacement phasors. A 3D Gaussian filter is then applied to the curl volumes to alleviate noise, followed by averaging samples in a 4x4x4 window to reduce volume size and computational time. The local frequency estimation algorithm is used to estimate the local spatial frequency of the shear wave propagation pattern at the excitation frequency. The phasors are filtered using a 6th-order Butterworth bandpass filter and a directional filter bank consisting of 6 K-space directional filters along the axial, lateral, and elevational directions. A radial filter bank comprising log-normal filters is applied to each directional component, providing a narrowband estimate of local frequency or multiple angular wave numbers. The angular wave number k is transformed to the elasticity E using equation 1, where ρ is the density of the tissue, cs is the local shear wave speed, φ is the excitation frequency, and lambda is the shear wave spatial wavelength. The authors apply their proposed method to 3 CIRS homogeneous liver fibrosis phantoms, a heterogeneous CIRS phantom with 4 different inclusions, and an ex vivo bovine liver sample. For the homogeneous phantom, volumetric RF data are collected using both PW and CDW imaging sequences, and the elasticity values are estimated and validated using the CIRS phantom manufacturer's elasticity values. For the heterogeneous phantom, RF data are acquired from 4 different regions, and the elasticity range of the inclusions reported by the manufacturer is used to validate the estimated elasticity values. For the ex vivo bovine liver, the experimental setup for the ultrafast SWAVE is described, and the sample dimensions and weight are provided. The matrix array transducer is placed on 7 marked locations on the sample, and the measurements are performed for each location by averaging within a 5 by 5 by 10 cubic millimeters ROI to avoid boundary artifacts. 2 excitation frequencies of 60 Hz and 100 Hz are used to vibrate the tissue, and the estimated elasticity values are validated using MRE and quasi-static compression testing. The experimental setup for the study on estimating tissue elasticity using ultrafast SWAVE involves both phantom and ex vivo studies, aiming to validate the proposed technique's accuracy and reliability. The ultrafast SWAVE setup utilizes a 5 MHz linear array transducer connected to an ultrafast ultrasound scanner, scanning the entire liver sample and providing elasticity volumes for all regions. In contrast, MRE and ARFI setups are presented, also scanning the whole liver sample for validation purposes. The validation process compares elasticity values estimated by ultrafast SWAVE with those obtained from MRE and ARFI methods. Results from phantom experiments demonstrate the accuracy and reliability of the ultrafast SWAVE method, with estimated elasticity values falling within the manufacturer's range for all excitation frequencies. The study's findings on 3D ultrafast shear wave absolute Vibro-Elastography using a matrix array transducer are presented in Figure 5, which displays displacement phasors for the 17.5 kPa phantom. Axial, lateral, and elevational displacement phasors are shown, with elasticity values estimated from these phasors compared to those obtained through different approaches. These include axial phasors only, axial, lateral, and elevational phasors without curl, and axial, lateral, and elevational phasors with curl. The incorporation of curl in 3D displacement phasors results in a closer elasticity value to the CIRS manufacturer reported value, accompanied by fewer artifacts in the elasticity volume compared to 1D displacement estimation and 3D displacements without curl. The research also explores a heterogeneous phantom, where both pulse wave, PW, and continuous wave Doppler, CDW, imaging sequences were utilized to collect volumetric data. Elasticity volumes for each excitation frequency were calculated, and the elasticity values of a 2x2x2 cubic millimeters region of interest, ROI, at the center of the inclusion and inside the background were averaged and compared to MRE values. The average error between the estimated values and the MRE values is 9% for the PW sequence and 6% for the CDW sequence, with the CDW sequence providing results closer to the MRE values. Figure 10 showcases the elasticity volumes for all inclusions at an excitation frequency of 400 Hz, while Figure 11 presents the elasticity values along the midline of the elasticity volume for different inclusions. The estimated values by the CDW sequence are found to be closer to the MRE values than those obtained with the PW sequence, and both of the proposed methods follow the MRE values more closely compared to the values reported by the manufacturer. The elasticity volumes for the homogeneous liver fibrosis CIRS phantoms are presented in Figure 6, showcasing results for 3 distinct phantoms with stiffness levels of 1.8 kPa, 7.8 kPa, and 17.5 kPa. Each subplot displays the elasticity volumes for a specific excitation frequency, comparing the outcomes of the plane wave, PW, sequence and compounded diverging wave, CDW, sequence. The elasticity volumes are calculated using the values along the midline of the volumes between 10 and 60 mm depth. The color bar is scaled in kPa, facilitating the visualization of the elasticity distribution within each phantom. The PW sequence and CDW sequence are evaluated side by side to assess their performance in capturing the elasticity patterns in the phantoms. The elasticity volumes for the 1.8 kPa phantom demonstrate a relatively uniform distribution of elasticity values, with both sequences producing similar patterns. In contrast, the elasticity volumes for the 7.8 kPa phantom exhibit a more heterogeneous distribution, with the CDW sequence capturing more pronounced variations in elasticity compared to the PW sequence. The elasticity volumes for the 17.5 kPa phantom display an even more complex pattern, with the CDW sequence revealing a more detailed structure of elasticity distribution. The comparison between the PW sequence and CDW sequence highlights the advantages of the latter in capturing the spatial variations in elasticity, particularly in stiffer phantoms. These results have significant implications for the development of elasticity imaging techniques, as they demonstrate the potential of compounded diverging wave sequences in accurately capturing the elasticity patterns in heterogeneous tissues, such as those found in liver fibrosis. The research applies 3D ultrafast shear wave absolute vibro-elastography using a matrix array transducer to estimate elasticity values in phantoms, providing insights into their mechanical properties. In Figure 7, the estimated elasticity values for 3 homogeneous CIRS phantoms are presented, with average and standard deviation (STD) values calculated along the midline of the transducer. The results show an average error of less than 8% and 5% for pulse wave (PW) and continuous wave Doppler (CDW) sequences, respectively, for all excitation frequencies, demonstrating the accuracy of the proposed method. Figure 8 illustrates the 3D reconstruction of elasticity volumes for a 7.8 kPa homogeneous phantom at an excitation frequency of 350 Hz, showcasing the potential of the proposed method in generating detailed images of tissue elasticity. The use of a matrix array transducer enables the acquisition of 3D displacement data, allowing for the calculation of shear wave speed and subsequently, tissue elasticity. The implementation of curl in the reconstruction process further improves the accuracy of the estimated elasticity values. This study contributes to the development of a non-invasive imaging technique capable of providing high-resolution elasticity maps in real time, significantly impacting the field of medical imaging and diagnostics. This research paper presents a comparative analysis of different elasticity reconstruction approaches for a 7.8 kPa phantom excited at 350 Hz. The results indicate that using 3D reconstruction with all axial, lateral, and elevational displacement volumes yields more accurate elasticity values compared to relying solely on the axial displacement phasor volume. Moreover, incorporating the curl of the 3 displacement volumes in the reconstruction process improves the accuracy of the estimated elasticity values. However, there is a discrepancy between the reported elasticity value by the manufacturer and the values obtained through these approaches, which may be attributed to variations in temperature, excitation frequency, or changes in the properties of the phantom material over time. In an ex vivo study, a bovine liver sample was imaged using 3 different methods: ultrafast SWAVE, MRE, and ARFI. The results show that all methods estimate the elasticity values of the liver tissue to be in the range of 3.04.5 kPa, with less than 11% difference between the ranges obtained by ultrafast SWAVE and MRE and ARFI methods. The discussion highlights the benefits of employing a novel real-time volumetric data acquisition based on the SWAVE technique, which measures 3D displacement fields over a volume and enhances the accuracy of estimated elasticity values. To fully utilize the potential of the proposed method, it is recommended to have at least one full spatial wavelength of the shear waves in axial, lateral, and elevational directions. The use of the curl operation in the elasticity reconstruction algorithm is also discussed, which aids in cancelling out the effect of compressional waves and results in more accurate elasticity values and lower standard deviations within homogeneous regions. Figure 10 presents the elasticity volumes for various inclusions embedded within a heterogeneous phantom, acquired using a 400 Hz excitation frequency and 2 imaging sequences: plane wave, PW, and compounded diverging wave, CDW. The figure consists of 8 subfigures, each displaying the elasticity volumes for one of the 4 inclusions, with PW results shown in subfigures A, C, E, and G, and CDW results in subfigures B, D, F, and H. The spherical inclusions, positioned at a depth of 10 mm to 20 mm with a diameter of 10 mm, corresponding to the transducer footprint size, are represented in units of kPa, as indicated by the value bar. The comparison between PW and CDW imaging sequences reveals differences in their ability to accurately reconstruct elasticity distributions within the heterogeneous phantom. This builds upon the previously introduced 3D ultrafast shear wave absolute Vibro-Elastography framework using a matrix array transducer, demonstrating the feasibility of this approach in estimating elasticity properties of inclusions within a heterogeneous medium. The use of both PW and CDW imaging sequences enables a comprehensive evaluation of the proposed method's performance under different excitation conditions. This study's outcomes have significant implications for the development of novel elastography techniques with improved accuracy and robustness. The paper introduces a novel real-time, three-dimensional imaging technique utilizing the SWAVE method for prostate cancer detection in diagnostic care. This approach aims to enhance the efficiency and accuracy of targeted prostate biopsies by integrating magnetic resonance imaging (MRI) data with ultrasound. The proposed method employs a matrix array transducer connected to a Verasonics ultrasound machine, enabling the acquisition of 100 RF volumes at frame rates of 2000 volumes per second. This significantly reduces the overall acquisition time to 0.05 seconds, compared to previous SWAVE studies that required 12 seconds and 2 seconds. The technique was validated on 3 liver fibrosis phantoms, demonstrating less than 8% and 5% differences in elasticity values between the proposed plane wave sequence and compounded diverging wave sequence, respectively, compared to the manufacturer-reported values. An ex vivo study on a bovine liver sample also showed less than 9% difference in the range of elasticity values provided by the proposed method, MRE, and ARFI. The paper also highlights the potential of this technique to improve the diagnostic accuracy and efficiency in prostate cancer detection, allowing for more precise targeted biopsies and potentially reducing unnecessary procedures. The authors emphasize the need for further clinical studies to fully assess the efficacy of this novel imaging technique. This research paper introduces a novel method for 3D ultrafast shear wave absolute Vibro-Elastography using a matrix array transducer. The proposed technique employs a multi-frequency approach to enhance the accuracy and reliability of elasticity measurements in various tissues, including the liver, prostate, and breast. The study highlights the importance of elasticity imaging in diagnosing and monitoring diseases such as non-alcoholic fatty liver disease, cirrhosis, and prostate cancer, emphasizing the potential of shear wave absolute vibroelastography for providing quantitative elasticity measurements in these contexts. The authors detailed their experimental setup, which includes a 3D imaging sequence using a matrix array transducer capable of producing high-frequency shear waves. They also describe the post-processing techniques used to analyze the data, including the application of a Gaussian filter and a least squares fitting algorithm to estimate the shear wave speed. The results of the study are presented in Figure 11, which shows the elasticity values of the midline of the volume versus the imaging depth for both plane wave, PW, and compounded diverging wave, CDW, imaging sequences. The findings indicate that the compounded diverging wave sequence provides more accurate and stable elasticity measurements compared to the plane wave sequence, particularly at deeper imaging depths. The paper also discusses the potential applications of this technology in various fields, including pediatric imaging, cardiovascular imaging, and cancer detection. It concludes by emphasizing the potential of this novel method for improving diagnostic accuracy and patient outcomes in a wide range of clinical contexts. The integration of magnetic resonance, MR, T2-weighted images with elasticity volumes is a crucial step in the visualization and analysis of anatomical details. This process enables researchers to overlay elasticity volumes calculated by the ultrafast SWAVE method onto the T2-weighted image volume, providing a comprehensive view of elasticity properties in conjunction with anatomical details. As demonstrated in Fig. 12, this overlay can be visualized in various planes, allowing for a detailed examination of the relationship between elasticity properties and anatomical structures. The ultrafast SWAVE method, which uses shear wave elastography to calculate tissue elasticity, plays a key role in this integration. By combining these two types of data, researchers can gain insights into the mechanical properties of tissues and their relationship to anatomical features. This integration is particularly significant in fields such as medical imaging and biomechanics, where understanding the interplay between tissue elasticity and anatomical structure is critical for diagnostic and therapeutic applications. For instance, in the context of cancer research, the overlay of elasticity volumes on T2-weighted images could help identify areas of abnormal tissue stiffness, potentially indicating malignant growths. Furthermore, this approach can also be applied to other imaging modalities, such as computed tomography, CORT, or ultrasound, to provide a more comprehensive understanding of tissue properties and their relationship to anatomical details. In conclusion, the integration of Mr. T2 weighted images with elasticity volumes offers a powerful tool for researchers and clinicians, enabling them to explore the complex interplay between tissue elasticity and anatomical structure in various contexts. The authors draw on a wealth of existing research in shear wave elastography, crawling wave sono-elastography, and single tracking location shear wave elasticity imaging for tissue characterization. They cite studies that have explored waveguide effects and their implications for cardiac magnetic resonance elastography, as well as the traveling wave expansion approach to the inverse problem of elasticity reconstruction. Additionally, they reference work on curl-based finite element reconstruction of the shear modulus without assuming local homogeneity, and the theoretical limitations of the elastic wave equation inversion for tissue elastography. This body of literature provides context for the author's own research on 3D ultrafast shear wave absolute Vibro-Elastography using a matrix array transducer. Moreover, the authors reference studies that have investigated viscoelastic shear properties of in vivo breast lesions measured by MR elastography, and reviewed Mr. elastography applications and recent developments. They also draw on research quantifying hepatic shear modulus in vivo using acoustic radiation force, and shear wave dispersion in lean versus steatotic rat livers. These studies underscore the importance of accurately measuring shear wave speed and elasticity in various tissues and applications. The author's research builds upon this foundation, focusing on the development of a novel method for 3D ultrafast shear wave absolute Vibro-Elastography using a matrix array transducer. This approach aims to improve the accuracy and efficiency of tissue elasticity measurements, with potential implications for diagnostic and therapeutic applications across multiple medical fields.